Okay, so let's pick up where we were at. It seems like forever since we've talked. So there were two problems from the exam that are going to motivate today's topic, or I guess topics, because there's technically two different things. So if you were to look at, if you recall with the exam, there were two problems that we sort of were trying to spell out or motivate some ideas. And so what we'll do is we'll look at them one at a time. So there was a problem, if you recall. So the first one was the following. So use trapezoids to approximate the area under the curve. So that was the first problem, I shouldn't say the first problem. This was problem 4 on your exam, and the purpose was to sort of maybe enlighten you or give you an idea of, the motivation for the integral was to use rectangles. And one of the things that rectangles don't capture is the rectangles, if you think about a curve being steep, a rectangle is not as good of an approximation as a trapezoid can be. And so that's going to motivate one topic. And then the other problem we looked at is we looked at taking the limit of a function of this form. So basically we're saying, okay, what if we took the limit as x goes to infinity of some expression like this? So now this is scary looking notation, but the problem 5 on the exam was motivating an idea of how this thing could work. So does anybody have any questions or comments about these ideas? Okay, so again, we had two problems on the exam. These were sort of what they were getting at. And so what we're going to do now is talk about them in a more specific sense. So approximating by trapezoids is a special case of what's called numerical or just numeric integration. So the adjective numeric, you can think of it as sort of compare it and contrast it to what we've been doing. What we've been doing to this point is we've really been doing symbolic integration. We're using mathematical symbols and some symbolic procedures to integrate. So let's sort of think about what we mean by that. So So let's consider an old friend of ours. Consider this integral, which we can easily compute by hand. So how do we compute this by hand? Well, the simplest way is to use what's called the fundamental theorem of calculus. And you write it like this, and then it's 1/3. Voila. So here's the catch. What makes the above computation easy? Of course, easy is a relative term. It took humans a heck of a long time to figure that out. But what makes it quote unquote easy is that the fundamental theorem of calculus applies because we know the antiderivative of x squared. So remember, the function we're trying to integrate is x squared, and since we readily know how to find its antiderivative, we know this procedure, that means we can do this sort of trick. So if we don't know an antiderivative, or if we didn't know, so let's phrase it that way. So if we didn't know the antiderivative, we have to use the definition which is a limit of a Riemann sum. So at first, this seems like it's bad news if you don't know the antiderivative, because what it's telling you is in order to compute a derivative, it's a very an integral, it's a very complicated idea. But if we don't necessarily look at it through that window, if we look at it from a different perspective, what it tells us is that, especially with technology on our side, we can easily approximate any integral using rectangles. So when we talk about, by the way, if it is worth pointing out, if for any other reason than to scare you, what the definition of an integral is. Remember, the definition of this for some function f is a limit that looks like this. And I'm not going to, these are all these symbols that you have seen numerous times now, dating way back to Calc 1, but that's the definition. And so what the definition suggests is it suggests that if you have access to things that compute and add real fast, then integration can be done to any desired level of accuracy you want. So it's worth pointing that out. So the definition says, and this is important if f of x is continuous, that we can always approximate the integral using rectangles. So what I mean by that is we can take an integral and we can always write it. Instead of taking a limit, let's just add up the heights. These are the heights and these are the widths of n rectangles. So if we draw the picture, let's just remind you of the geometric intuition here. So let's pick a simple scenario here. So if I have this curve and suppose I'm interested in what's happening from, say, A to B, well, if I use 4 rectangles, here's what we're saying. So you guys might remember I can use a left Riemann sum, which uses these guys as the heights. So if I choose to use that, then my rectangle looks like this. And then I have one that looks like this. I have one that looks like this. Looks like this. And of course, I got to fill in these cracks. But so the geometric intuition is that the area of these 4 red rectangles, so this would be here, this is the case, n is 4. The idea is that the area of those 4 rectangles is approximately the area under the graph. Now, of course, you would say, of course, I see air there. And yeah, there's air there, and that's okay. But what we do know is our intuition even tells us is that if we increase from 4 to maybe 8 or to 20 or to 1,000 rectangles, then that air is going to shrink. And we know that in the limit of the number of rectangles, we get a value. We see a limiting value. So this is good news. But the bad news is that if you want accurate results, you need lots of rectangles. So before we do anything, does anybody have a question about this? So let's make a point of what I just said, because that's important. So the good news is the above approximation always works. What's the bad news? Well, the bad news is to achieve a desired level of accuracy, you might need very large, let's say this way, a very large number of rectangles. Now, of course, you might say, I don't care because I have a computer and I know simple computer science and I can program. Look, if we go back a page, it's not difficult whatsoever to program a computer to do this. In fact, if you've had even a little bit of experience using something like Python or MATLAB or Octave or even Excel, this is not difficult to do. However, as mathematicians, we're always looking for more efficient and better ways of doing things. And so what we were trying to motivate on the midterm is that instead of using a rectangle, why not try trapezoids? So sort of, if we look at this good news and bad news, we might say, okay, what about another shape? So what do I mean by what about another shape? Well, let's draw a picture. So if we go to the next page, so let's draw a curve. So what if it looks like this? And so let's just drawing some arbitrary function. Let's call this point A. Let's call this B, and let's just look at having two whatever shapes. So if we had a rectangle, so let's draw a rectangle in red. And let's say I use a left Riemann sum. So if I use a left Riemann sum, what I have is this. So the red is a left Riemann sum. Now, instead of using that, let's use a different color. Let's take this green, and instead of using two rectangles, let's steal this point in this line, but then let's draw a straight line from here to here, and then let's draw this straight down. And then let's draw this line from here to here, and then draw this straight down. And now I have green, which is trapezoids. Now, if I shade in my red, if I look at these two red rectangles, you could argue that they are sort of approximating the area under the blue curve. But even a fifth grader will come right in and tell you, because it's intuitive, is that if I use this extra triangle and put it on top of the rectangle, as with this one, or if I use this trapezoid in this trapezoid, and we're going to label these points for a second and state what the fifth grader would say. So this is the point A. So this is the point A, comma, f of A. This is the point B, comma, f of B. And let's just call this guy, for lack of a better name, we'll just call it x sub 1. So this is x sub 1, comma, f evaluated at x sub 1. And don't forget, we often refer to A as x sub 0, and we refer to B as x sub, in this case, 2. So if we merely look at this picture, we can make some conclusions. Before I write down what I want you to see, does anybody have a question, comment, concern? Okay, so here's what I want you to think about. Do not think calculus right now, other than what I guess the symbol, but try to think just 5th grade mind. What's bigger? And so what this picture tells me, and if we remind ourselves of what these things are, what's this distance? This is delta x. And so what can we say? Well, what's the area of the first rectangle? The area of the first rectangle, its height is f of a, but I'm going to write it as f of x of 0. So what I have is f evaluated at x sub 0 plus f evaluated at x sub 1 delta x. Whoa. This is clearly less than. So, by the way, if you're not picking up what this is, what is this right here? This is the height, or the area of the 2 rectangles. Heights and widths. So that's clearly less than, I guess, or equal to. Now, what is the area of the trapezoids? Well, you might have to Google that. Maybe you guys don't necessarily remember the formula for the area of a trapezoid, but it's not hard to derive. Let's draw it in green since we already have it in green. So the area of this we'll be very careful. So the first trapezoid has height A, or excuse me, height f of a. So the way we write this is we'll write this as f evaluated at x sub 0 plus f evaluated at x sub 1 all over 2 delta x. That's the first trapezoid. And then the second trapezoid has this as its area. So this is the area of the trapezoids. And what we clearly can see is in this particular drawing is that that area is less than the area under the curve. And so we know that the area under the curve is exactly equal to this particular integral. So again, I want you to think the red rectangles take up less space than the green trapezoids, and the green trapezoids take up less space than the actual area under the curve. And so if we wanted to be real technical, we could even do this instead of doing 2 rectangles or 2 trapezoids, we can do it for n of them. And then we might even be even more brave and take a limit. And so what we can find out now, as your intuition tells you, is that these trapezoids can often be a better way of approximating the area under the curve. Not all the times, but often. Does anybody have a question? Okay, so what is the moral of this picture? So the moral is the following. In some situations, using trapezoids can be more efficient than rectangles when approximating integrals. So because of this, we have what's called the trapezoid rule. So I'm not going to go through the algebra, but if you go back to the previous page, what you'll notice is we could simplify what's in the green. Notice that I have two f of x1s, and I could do some algebra to write that a little more compactly. And maybe it would be a good exercise for you to do that. And so I'm going to hope that you do. And hopefully you can readily derive the following formula. So this technique is called the trapezoid rule. So what does the trapezoid rule say? It says that this integral that we know and love, a of b of f of x dx, we can approximate it in the following manner. We can write it as 1/2 delta x, and then it's f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2. And this pattern continues. And you'll notice that this is easy to memorize because everybody has a 2 in front of it except the first and the last guy. So this is a very scary formula, but once you use it a couple times, it's not difficult. We're going to do that right now. So don't forget what all these creatures are. What is delta x? Delta x is b minus a over 2. And what is x sub n? Or I guess we should write it more carefully. X sub k, we'll call them in general, is a plus k delta x. So for example, when k is 0, you get x sub 0 is a. When k is 1, you get a plus delta x. So this is all, these subscripts, this is what we've been doing since we first defined the integral way back in Calculus 1. All right, so let's look at this for a specific example. Does anybody have a question or comment before we do this? Going once. Going twice. Is everybody alive? Do I have to call the authorities to check in on everybody? Ooh. All right. So let's see how this thing can be done. Oh, so much time in there. Could be something. That's good, Zach. Very nice, Zach. You guys know I'm kidding, right? I kind of imagine that, like, if I were in your shoes, I would probably just log in and take a nap. Although then again, I don't know. Who knows? It's kind of too hot to be outside anyhow. All right, so let's do some examples because you guys love examples. So here we go. So let's approximate the integral we did before. We know the exact value of this, so we'll practice on it. In the real world, this numerical integration is useful for really complicated integrals that we might not be able to do by hand. And there's many other places where this becomes very useful. But, you know, we're going to practice it right now on a simple integral whose value we know. Then we can, you know, we look at our results and we say, okay, maybe we're doing it right. Maybe we're okay here. So let's approximate this using the trapezoid rule. For n equals, we'll do it first for n equals 1, then we'll do it 2, then we'll do it 4, and then we'll do it 10. Now, you might think that this is going to be tedious, and it is, but we do have calculators that can help us. And also, if you're brave and you know you say I'm going to be an engineer, or I'm going to be a certain type of I'm going to be a computer science major, then you should really think about learning how to write this in, say, Python or MATLAB or something, and I'd be happy to help you. It's like 2 lines of code. But anyhow, we'll do it by hand because you got to start by hand. So let's do that. So let's recall our rule. Here's what we know. We know that, and it can't hurt to just write it down a few times is to not mess it up over and over again. You don't want to do that. So let's recall this integral by the trapezoid rule is 1/2 delta x, and then of course it's going to be f evaluated at x sub 0 plus 2 times f of x sub 1. It's an ugly formula, but it has symmetry, and we like that. So what are our functions here? So let's make sure we're all on the same page. So for this particular one, delta x is just 1 over n, and f of x, of course, is x squared. And then your x sub 0 is equal to 0, x sub 1 is 1 over n, etc. Excuse me, not 1 over. Yeah, 1 over n, excuse me. So again, we're going to take this area under the curve. We're going to approximate it with one trapezoid. Then we're going to do it with 2, 4, and then 10, just for fun. And again, using a calculator, even with 10, it doesn't take long. Okay, so let's do it. Here's the case when n equals 1. When n equals 1, your delta x is 1. You only have two guys. You have x sub 0, which is 0. X sub 1 is 1. And so you get that the integral from 0 to 1 of x squared dx is approximately 1/2 times 1. And then it's times f evaluated at 0 plus f evaluated at 1. Which simplifies to nothing more than 1/2. So that is not the exact answer. We know the exact answer is 1/3, but that is an approximation using one trapezoid. Now, if you drew the pictures, it's not going to surprise you because all you're doing is calculating the area of a triangle. Does anybody have a question, comment? Okay, so let's do the next case. We'll switch colors. It'll be very... So the next one is when n equals 2. When n equals 2, your delta x is 1/2. And so it might be useful if you want to see your interval. If you want to use two guys, how do you break your interval up? It's 0, 1, 1/2. And so this is x sub 0. This is x sub 1. This is x sub 2. That might be helpful as well. So the integral becomes 1/2 and then times delta x, which is 1/2. And then it's f of 0 plus 2 times f of 1/2, and then plus f of 1. Now, if you go to a calculator and you add this up, well, what do you get? Well, let's go break it down real quickly. This is 1/4 times, this is 0 squared plus 2 times 1/2 squared plus 1 squared. So you have 1/4 times 1/2 plus 1. So that's 1/4. And so you get 3/8. But of course, if you round that, if you write it as a decimal, what that is that's 0.375. So our first approximation was 1/2. Now we're at 0.375. Any questions, comments? All right, so what was the next thing? We said 1, 2, I think 4, and then 10, yeah. So now we have to do 4 rectangles. So when n equals 4, your delta x is 1/4. If you want to figure out your x sub i's, your x sub k's, you break it into 4 pieces. So this is 1/4, 2/4, 3/4. And so this is approximately 1/4 times, or excuse me, it's 1/2 times 1/4. Let's not mess up our. And then once again, it's f of 0 plus 2 times f of a 4th. You leaving? Hold on, gang, hold on. Okay. All right, gang. Sorry about that. I have a typo here. There should not be a square there yet. All right, so we have to make sure we put the 2's in front of everybody that gets a 2. All right. So try to go a little quicker here. This is 1/8 out front, and then 0 is squared is 0. So you're left with 0 plus 2 times a 16th plus 2 times 4/16 plus 2 times 9/16. And there's lots of patterns here. But if you do the arithmetic and you do it properly, and again, I hope that you fill in these details on your own, but I can't force you. So if you add all this up on a calculator, what you end up getting is 0.34375. And then lastly, if you do it with 10, and again, I hope that you fill in the details. Let's change colors. So for n equals 10, you end up getting this. Hopefully you guys can do the computation and you'll get the same thing I get. You get 0.335. So if we make a little table here to illustrate our results, what's happening. This is often useful to do. So if we have our n values here, and then we have the value of the integral, the approximate value. I guess we should draw it the other way. So when n is 1, we got 1/2. When n is 2, what did we get? We got 0.375. And then when n is 4, we got 0.34375. And then when n is 10, you get 0.335. So the point is as n increases, that number on the right is going to, as you expect, converge to a third. Does anybody have a question or a comment? Going once, going twice. Okay, so far what we've said is that rectangles get the job done, but it seems like trapezoids in many scenarios would be much better. And if you want to see that for yourself, you should do a left or right Riemann sum with the same number of rectangles, 1, 2, 4, and 10. Maybe make a chart. Does anybody have a question, comment? Okay. So the next question then becomes, what about, can we do better? So is there something that's even more efficient than trapezoids? And it turns out that oftentimes there is. And one of the standard algorithms, if you will, is what's called Simpson's rule. So, and then we're not going to go into all the calculation because it's a lot of tedious algebra and some tedious calculus, but the formula is very simple. So what is Simpson's rule? Well, Simpson's rule says instead of using straight lines to connect these points, why don't we use parabolas? So Simpson's rule is a little more sophisticated, but it's very, very useful. So what does Simpson's rule say? It says that the integral from a to b of f of x dx can be approximated using this pattern. 1/3 dx, and then it's f evaluated at x sub 0 plus. Now this pattern's a little different. Instead of being 2's in the middle, it alternates between 4 and 2. So this pattern's a little more sophisticated, but it's very symmetric. So once again, the first and last guy do not have a coefficient in front of it. And the guys in the middle all alternate between 2 and 4. So notice the first one is 4, then 2, then 4, and it alternates. So here, what's important, for this to work, n must be even. If n's not even, that pattern doesn't make any sense. but everything else is the same as in the previous, the previous approximation and in your left and right Riemann sums. Now again, the derivation of this formula is a little more complicated than the trapezoid derivation that we did. The trapezoid one is not very difficult to derive. This one, it's not that it's difficult, it's just tedious. And so we're not going to do it, but it's in the book, it's on the internet. And if you're so inclined, you should think about doing it. Does anybody have a question? Comments? So really what this comes down to is this comes down to you plugging numbers into a calculator. Now, you might then say, well, this is silly. Why are we even doing this? Well, again, you have to understand these basic ones because how is this stuff used in the real world? This stuff is used in the real world all the time when usually when we use these things, we're using fancy software to write programs that use these sort of tools. And so some of you will get to learn all these things in other classes. Some of you will get to use these things. There's a whole branch of math called numerical analysis, and people spend their career studying things in there, and the questions they try to answer are, how accurate do I have to be? Or let me rephrase that. How big should n be so that I'm this accurate or I'm that accurate? How do I know if I'm within 2 decimal places of accuracy? How do I know if I'm within 20 decimal places of accuracy? So what people do is they study what we call error analysis. They study the error. And so again, some of you will go into classes where you'll get to do that kind of stuff. Some of you will never see it again after this, and that's okay. Another place that this kind of stuff is used all the time is in discrete worlds where we don't have continuous data, but maybe we have discrete data, like things like the stock market or things like population, or we take daily temperatures. So if our data is not continuous, because we're measuring it, say, well then how do we approximate it? One way we can approximate data in certain aspects of it is using these tools. Does anybody have a question, a comment? Okay. So let me reiterate something that is also extremely important. Many integrals we encounter outside of class. So in the real world, you know, when we're building things and we're engineering and we're doing physics or whatever it is we might be doing. So many integrals that we encounter outside of class can't be evaluated analytically by hand. We must use numeric integration. So if these two sentences are confusing to you, well, what I would ask you to do is to do the following. Suppose I asked you to compute this creature, or this creature. Both of these integrals are very important in real-world applications. Think about, can you integrate them by hand? What about something like this? So just think, could you compute these? Could you find an antiderivative and do parts, or could you use substitution to integrate them? And the answer is, for all three of these, is no, you can't. So if you want to know the value of these, you have to use some sort of technique similar to what we've been talking about, numeric integration. Okay, any questions or comments? The other thing you can do, and we're going to ask you to do this on homework, is so we can use numeric integration to determine the value of certain numbers. So we asked you to do this on the exam. If you remember, we told you the log of 2 is equal to the integral from 1 to 2 of 1 over x dx. So you might ask yourself, how did human beings know what the log of 2 equaled before calculators? Well, one way that you could approximate it is to approximate that integral using trapezoid or Simpson's rule. Another famous number you can, get its value by using integration is this guy, pi. Does anybody have a question, comment? So what we'll do, one of the questions we'll ask you to do is we'll ask you, just like on the exam, we asked you to do the first one up there, But the bottom one comes from, again, if you're confused how I'm getting these formulas, all I'm doing is if you integrate, look at the integrals and compute the integrals using the symbolic argument. What's the integral of 1 over x? Well, it's log. So you get log 2 minus log 1, which is log 2. And then if you do the bottom integral, that integral is the arctan. So you get the arctan of 1 minus the arctan of 0. Well, the arctan of 1 is pi over 4. The arctan of 0 is 0. So that's why those are true. Okay. Does anybody have any comments or questions? Okay, so we're going to switch gears slightly, and we're almost done, I promise. We do want to get this in here so you guys can get working on these, and that way you have questions you can ask. So, our next topic is called improper integrals. So we motivated this on the test as well. So long story short, it's useful to have a definition for this. So typically we have the integral from a to b, but turns out just for mathematical fun and for real world problems, it's useful to ask, can we integrate up to infinity, or if our upper bound is infinite? So I could give you lots of explanations why. We could talk about physical problems if we wanted. We could just say, just the joy of math. We want to make a definition here. But note that if we want to make this definition, it currently makes no sense, because in order for an integral to have any meaning, it doesn't have any meaning unless you have a number in the bottom and a number at the top, because we need to define that delta x. Delta x is b minus a over n. What in the world is infinity minus a over n? It doesn't make any sense. So what we do is we think about what it should mean if it were going to make sense, and that's what we tried to do on the homework, excuse me, on the exam. We tried to give you a problem that illustrated what happens to certain integrals if we let the upper bound get larger and larger and larger. So if I tell you to refer back to problem 5 on the midterm, you might make sense of the following. So what we do is we make the following definition. This new symbol, the integral from a to infinity, not a to b, a to infinity. So now we have this symbol, the infinity symbol is our upper bound. This is, by definition, the following limit. If it exists. So if it does exist, we say the integral converges. So that's a word you're going to start hearing over and over again, converges. We're going to use it a lot. So let's just crack open an example real quick to see that this is actually not that difficult. It's a little, well, it's actually, I shouldn't say that, it's funny because I think it's not difficult, but then for some reason, this is a topic that students are always baffled by. It's very strange, but I guess such is learning. So if we wanted to compute, say, the integral from 1 to infinity of 1 over x to the third power, does it converge? What we have to do is we have to write out what it means and see, does the limit exist? The first thing I would do is I would rewrite this as x to the -3, just because my brain likes that more. And then I replace infinity with a t, and I do the integral. So the integral, I add 1, so this is negative, and then it's, you add 1 and divide by the new guy. So maybe I'll be a little more clear. What's -3 plus 1? -3 plus 1 is -2, so you end up getting x to the -2 over -2, and you're evaluating this from 1 to t. And so how do you want to think about this? Well, if you plug in t, so one way, if we write it out a little more clearly, this is 1 over -2t squared. And then it becomes minus a minus, which is plus 1 over 2. And so, of course, this limit equals 0 plus 1/2, which is 1/2. So we say the limit converges. Or excuse me, we say the integral converges. Does anybody have a question? Concern? So this is one type of what we call an improper integral. Running out of slides. There's other types as well. So we can also define, suppose we wanted to go from -infinity to some fixed number. How would we do that? Well, it's just almost identical. You might say, you just write it like this. You put the t downstairs and integrate like that. And then another very important integral is, what if we integrate over every real number? How do we define this? Well, the correct way to define this is you have to define it as two limits. So the first thing you'll do is you'll define it as maybe the limit as a goes to -infinity of a to 0. This is one way of doing it. Plus the integral from 0 to b. We have to take a limit. I'm getting ahead of myself. So these are two more improper integrals. And let's be very clear. I mean, these things don't make sense unless f is continuous. So let's just assume that we're assuming f is continuous. Okay, and then there's one more type of improper integral that we need to define. And again, we're assigning meaning to things that shouldn't mean anything, but we're assigning it in an intuitive way. And so I know this is sort of a sophisticated idea, or maybe this is all scary formulas and stuff. I understand it. I've been there before. I mean, don't forget, I once sat in well, back then I sat in a room and listened to someone talk about all this. But look, the stuff can be overwhelming. But the best thing I can tell you is work on the homework. And if you can't do them, or you don't even know where to start, you got to ask. So the last thing we'll do is we'll define another scenario. So another type of improper integral occurs when the function has an asymptote. At, say, x equals a. So if it has an asymptote at, say, x equals a, then how do we assign meaning to this? This doesn't make any sense, because if we say it has an asymptote at a, that means that f of a is undefined. So that means we have that asymptote. It's unbounded. And so how do we make any sense of this? Well, what we do is we have to think of it in terms of a limit. Instead of integrating from a to b, we'll integrate from some variable. Let's call it, one way to do this is we might use the Greek letter delta, and then we'll let delta approach a from the right. So again, what we're doing is we're assigning meaning to something. This notation that I have written on the left-hand side, by the definition of the integral, it's meaningless, because I can't even write out the Riemann sum. However, if I define it to mean this, then it does make sense. All right, so anyhow, what we're going to do is we're going to give you some problems to work on this, and hopefully you do, and you ask questions by Thursday or Thursday in class. Does anybody have any questions right now? Comments, concerns? All right, so then I will say let's talk again Thursday. Feel free to blow my email up and scream and yell until I upload your grades. Please know I'm sorry. I know some of you have emailed me. Continue to do it. I will not be mad. And then I will talk to you guys Thursday, if not sooner. So take care. Thank you for joining me. And if you have any questions, be not afraid to ask. All right, now, bye.